So welcome to this second colloquium of the year 2024. And I would like to start by really thanking my colleague, Professor Antonino Cattaneo, for proposing something that is outside the direction that we cover. We don't teach geophysics, and so we will all learn more than hearing something in our own fields. One question that came to my mind is why a biologist should be interested in problems with climate change and the poles. And the best answer I could come with is that it's the prerequisite of biology that the world doesn't fall apart. No? So otherwise, you won't be able to do it. Please.
So thank you, Augusto, and welcome to everyone. So it's a welcome today our speaker, Carlo Barbante. He's the director of the Institute of Polar Sciences in the National Research Council and the full professor at Foscari in Venice. And he has been involved for years on climate change and climate and environmental reconstructions. And he will tell us about his deep interest in polar sciences. Poles are not only have a huge influence on all our climate and Earth system, but also are, from my perspective, a very nice readout of the consequences of climate change. So you can measure things as we shall hear. So I had two reasons for suggesting Carlo Barbante as a speaker for these subjects, because one is institutional. I think that in a place like Scuola Normale, it is very important that we get exposed to earth sciences and the climate sciences. And the second one is a personal reason. I have heard on at least two occasions Carlo conferences, and this resonated with a very, very deep and old interest that I have in reading about polar sciences. And there is just one anecdote that I would like to say, that I am very fond of one explorer that is Fridtjof Nansen. And I learned quite recently that before his first polar exploration, when he made the first crossing of Groenland, 2 days before he took his PhD, and his PhD was in neurosciences. So I'm a neuroscientist, so this is a very deep connection. And in neuroscience, I'm talking now to my students, he made his PhD thesis, at the time in which Cahal and Golgi were discussing about the reticular or the neuronal theory of the brain, he was the first who took part in favor of the neuronal theory. So anyway, Carlo Barbante will talk us today about climate changes and the poles matter. And I really thank you for coming here, and we look forward to your talk.
Thank you. Thank you very much. Thanks for the kind introduction. And it's really a pleasure and honor to be here in this wonderful room to give this seminar. Well, I'm going to speak about the poles, polar regions. And the reason for that is that basically I can resume that saying that what happened in the pole doesn't stay in the poles and reverberate all over the world. Yes, well, this is a big exaggerated image of the two poles, the North Poles and the South Poles, and there are some similarities in between these two regions. They are, of course, both center into the geographic pole. Both have cold winters and well, I would say cool summers. So it's not really real summer what you have over there. There are glaciers, there are snow and whatever, but they are quite different. And the main difference for that is that while the Arctic is populated with mammals, especially land mammals like polar bears and foxes and deers and things like this, the Antarctica is totally empty of terrestrial mammals. Whatever you have in Antarctica is connected with the life on the sea. And then another another big difference is that the Arctic is an ocean covered by a tiny layer of ice, sea ice, and all the continents are surrounding this area, while Antarctica is a real continent with an ice sheet on top. Somewhere, in some places, it can be up to 4 kilometers thick. So basically, it is something which is extremely important, and the main reason why the poles matter, I can summarize in these 5 points, and there is a sixth one that I will tell at the end, and this science diplomacy. Polar regions are so far places of peace and science where we collaborate literally with all over the world. So briefly, the poles are pillars of climate science. Arctic especially is warming 3 times faster than the rest of the world, and that's something incredibly important. The Arctic is very complex. You see here more or less many different cycles that can happen into the Arctic in this case, and these regions are really literally hotspot of anthropogenic changes. There are phenomena that are accelerated a lot in polar region, especially when we speak about sea ice. Then biodiversity. Polar regions are losing biodiversity at a very high speed, and that's something in which we have literally deepen our knowledge into the future. And then most of the known tipping points are located in climate region. Tipping points are critical threshold in the climate system that has been overtaken in the last few decades, and most of them are located in the polar region. And then, as I say, it is also a place of science, and there are a lot, is an open laboratory. Polar region are open laboratories for a lot of studies, and especially for climate science. And I will give you a brief example. Well, most of the things I'm going to tell you, not all, but at least a good part, if you want to have a resume of what is happening in the cryosphere, is inside this IPCC report. IPCC stands for Intergovernmental Panel on Climate Change, and that we publish within that a special report on ocean and cryosphere. Well, again, going to look at the pillar of climate science, as I anticipated. Well, it is clear what is happening since the beginning of the 20th century, even slightly before that the CO2 concentration is increasing dramatically, about 50% more since 1750, so is a huge increase. Of course, there are seasonal cycles, as you see here on the left side, and seasonal cycles are tightly linked to the fact that during summertime the vegetation is absorbing a lot of CO2 from the atmosphere, and therefore concentration is lower. And then, but what you see in black is that the average concentration of CO2 is increasing very quickly and constantly, with some holes maybe given to the gas crisis, given to the COVID and so on, but the tendency is that one. And so the interlinking between greenhouse gases concentration and the temperature is today undisputable. So nobody is disputing and discussing about the cause-effect interrelationship. And if you see what happened during the last 150 years, this is the global temperature change, and we keep it as a reference, the period of time 1971-2000. Whatever is above is a positive anomaly, and whatever is below is a negative anomaly. But if you keep that, you see that the warming is incredibly rapid, especially over the last 4 decades. And we had never had something like that in the last 2,000 years, if we go back in time looking at archives of climate. Well, this is an average. The increase in temperature, if we compare today average temperature with the temperature we had before the industrial period, is about 1.3 degrees higher. But that is not equally distributed all over the world, because if you look at these and you see time is passing over the figure here, you see the differences in temperature. We today we can measure temperature very accurately all over the world. You see there are places which are warming faster than others, and especially if you look at the North Pole and in the Arctic, there are very, very large portion of the Arctic which is warming at a very high pace. So it's warming incredibly high. And since the last 2 decades, also the Antarctic, especially in the Antarctic Peninsula, the West Antarctic is warming with clear consequences on the cryosphere. Well, as I said in one of my first slides, I told you that the Arctic is warming at a pace which is about 3 times the rest of the world, with dramatic consequences. We know it quite well. We know what happened. We know what happened also in the past. You have a reconstruction here with different time frame of the last 60 million years of the climate. We have on the bottom panel, we have the temperature, reconstructed temperature, and we have the CO2, atmospheric CO2 concentration on the top. So you see the clear interlink of the CO2 and temperature over the last 60 million years. Consider that 60 million years ago we had no ice on Earth, so the temperature was too high, about 15 degrees higher than it is today, as it is here. But then, of course, this is part of a general cooling trend. It works like a thermostat that you have in your house, you know. CO2 is regulating climate over long time scale, and this is exactly what is happening here. Overimposed to this, we do have a fluctuation which are tightly linked to orbital parameters, so the amount of energy that arrive into the surface of the Earth. And then we have the future, and the future is here more or less with the current trend, with the current increase in the temperature that we have seen before, the dramatic increase in CO2 plus 50% over the last century, and the projection into the future. This is what yeah, I told that the scale is different in the... No, the scale is the same in this panel, and the scale is the same on the top. On the top panel, the scale is always the same. So those on the right are simulation, are climate models, that are based on the data. And of course, climate models are tested on paleo data, so we can reproduce with climate model what happened in the past. So, well, this is the chance to go down. I mean, this is the best scenario. Will at least stabilize climate. Not by itself, of course. Well, by itself, if we stop emitting CO2 tomorrow. Yeah, that's what we should do. Well, we will come back to that with scenarios. But anyway, it's just to tell you that things happen, and there is a lot of our past in our future, because, well, with concentration of about today we are at about 420 parts per million. We have to go back in time at least 2 million years to have concentration of CO2 similar to the one that we have today. But if you look at the temperature, we are definitely at a higher value than we have today. And this, as I said, has a lot of implication on, especially on polar region. It is quite well known. I mean that Sicuro Manabe wants in 2021 the Nobel Prize for his studies on global warming, and especially on warming of the tropospheric of the troposphere. This was then simulated in most recent years with modern models that exactly replicate what was already foreseen in the 80s by Manabe in the 80s. But even better and even more interestingly, the work of the Nobel Prize could calculate the what we call the Arctic amplification. We have seen that the Arctic is warming faster than the rest of the planet, and in fact, if you look at that, and this is a projection in years from up to 95 years from, well, it was in the paper of the 80s, and this is the latitude here on the left side, you see that the northern latitude, the temperature is higher. And this is due to many different feedback effects that accelerate an initial warming. Plus 6 degrees. Well, it was a bit, I'll show you most recent calculation today. This is a simulation done by the group in Bern by Thomas Stoker and co-workers, where they simulate from the 50 to 2020 the warming of the Arctic, which is not on the same scale, is less than the 7 degree initially Manabe calculated. But well, it's still present. There are a lot of processes going on warming the Arctic, and this makes a big difference. So there are what we call the polar facts. We know that the CO2 concentration is increasing. We know it because we extract data from ice cores. So we drill deep ice core down to the bedrock. We can go back in time several hundred of thousands of years. The longest record is 800,000 years long and cover a long period of time. And inside the little tiny bubble that are entrapped into the ice core, we can reconstruct the composition of the atmosphere. And well, from the matrix itself, from the water, from the frozen water, we can have information about the temperature of the past. So on the same archive, we have both forcing and response factors, the CO2, dust, and the temperature of the past. Well, this is more or less how we work with that. We do drill ice core. We have several methods, but the most important one is the one that you see on the right, where you can go deeper and deeper and deeper. The longest record in terms of depth has been retrieved in Vostok in Antarctica, and is 3.6 kilometers long, 400,000 years of a complete history of our climate. We can do even better than that because, again, in a European project in 2006, we recover what is today considered the longest record of the ice core. It was more or less where the Harrow is now, in a place called Concordia, where we have a perfect stratification, the snow falling year after year, accumulating and trapping the bubbles and the CO2 and many different species into the ice. So we went there, we drilled down to the bedrock, we reconstruct the climate for 800,000 years, including the CO2 concentration that follow very well the temperature curve, except that, well, if you go up and you see what is happening into the most recent years, you see that the huge increase of the CO2 due to anthropogenic activity. This is definitely a great proof that we are contaminating our environment. Well, the polar region are also hotspot of anthropogenic change. One of the most important things that we can see is tightly linked to sea ice and, of course, to melting of the continental ice. If you look at the sea ice, well, it is something that is also very well known. It's the fastest rate, at least in the last 3,000 years. Arctic is melting very quickly. We are melting the continental ice. Okay, this is Antarctica, rivers of water flowing from the inner part of Antarctica and arriving into the ocean. That is something that started to happen about 20 years ago in Antarctica. We never seen it before, for at least for the last 100 years, when we have direct measurements, but even before from the paleo record. And it's even more in Greenland, because if you look what is happening in Greenland, and since the year 2000 we have a constellation of satellite that measure the gravimetry of the land and allow us to measure the what we call the mass balance, how much ice is precipitating, how much snow is precipitating, and how much ice and water is melting, ice is melting from the continent. And as you see, we have continuous loss of ice from Greenland, continuously since the year 2000, even before, but we have no satellite measurement before, we simply have direct measurements, especially on the coast, but also in the center of the Greenland is a negative mass balance. And Greenland is losing mass, especially from melting at the surface, but also melting on the huge ice shelf at the coast. So we have a huge loss of mass. If you calculate how much ice is Greenland is losing, is about 270 gigaton of ice per year, which is equivalent to nearly 1 millimeter of increased sea level rise on the total of the globe. Well, to make things even easier, the melting of ice in Greenland could fill about 420 swimming pools every minute. And this is every minute of the day. So that's a huge amount of water. And imagine a huge amount of water that goes into the North Atlantic, changing completely the density of the water. We have cold and light, low salinity water that have a lot of implication into the global circulation. Well, of course, continental ice increase and has a strong influence on the sea level rise. And in fact, since the year 1990, we have a satellite measuring the average sea level, and if you see, the increase of sea level was quite constant during the previous century. It was about less than 2 millimeters per year overall, but in the most recent year, if you look at that, it increased and increased and increased, and in the most recent years, since the last 10 years, is growing up at the speed of nearly 5 millimeters per year. So 5 millimeters is something like that. If you multiply by 10, you multiply by 100, you start to have, if it keeps a linear progression at a very, very high. Please? How easy is it to measure that now? It's quite easy because we have a constellation of satellite flying over the world, making a lot of acquisition. Then we have data on mareograph, direct measurement on site, spread all over the world. So the accuracy and the precision of this measurement is very, very high. So that's an average increase. Well, so if you look at the pace of these from 1900 to nearly today, we went to the pretty constant rate for about 100 years, but since 90s or even before, I mean, the increase of the velocity is really dramatic. Imagine a city like Venice or Pisa as well, you know, with an increase in sea level of such a velocity. Well, again, another aspect of that is the sea ice. Sea ice is another crucial parameter. Is the lowest level in the last 1,000 years. We see again from satellite measurements, and if you look what happened during the last 40 years, about 40 years, we see that the surface of the Arctic shrink very, very quickly. Losing about 40% of the sea ice surface in less than 40 years. So is decreasing dramatically. And in the last 2 decades, it went even faster than before. It's not just the surface which is shrinking, but it's also the thickness. And the thickness is decreasing very, very quickly during the last, especially during the last few decades. And I want to show you first a graph that show the area, how the area is shrinking, but also how the thickness of the ice is shrinking. This is a very young sea ice, which is a 1 or 2 year old, up to more than 4 years old, and you see that the ice that is 4 years old is about 3 meters thick. And if you consider with the time passing in the year 90s, in the year 2000, 2010, the the thickness of the ice is decreasing and decreasing and decreasing, as it is the surface. So you open many places around the Arctic, you open to navigation many places around the Arctic. So what was really a dream in the 19th century, the Western Passage and things like this, today is a reality. And there are already a lot of convoys, ship convoys that travel through North Siberia or Northern Canada to go on one side or to the other one. So it's quite common today to have, especially during the last part of summer, so August, September. So ice is literally shrinking both in surface and in thickness. And if you look at that, virtually you have no longer old ice. The ice older than 3 years is almost completely gone. Well, and of course, I read many articles about sea ice in the past, but well, and I read also when I was a boy and a young boy, a lot of books. And as Antonino said before, we all felt in love with explorers and people passing, trying to reach the North Pole. And this is what we have in mind. So when we speak about the Arctic, very thick ice that trap the boats and the ships and makes a lot of problem to the people. But this year, I went for the first time to the North Pole with an icebreaker. This is a time lapse of the last 5 kilometers reaching the pole, reaching the North Pole. I just want to show you what is the sea ice in the North Pole. When up to 40 years ago, it was about 3 to 4 meters. We went with this icebreaker. I'm sorry, it's a bit interrupted the time lapse, but we went through open sea, open sea. And when we found ice, well, it was nearly nothing, just 60 centimeters of ice. That with a ship like this, it was really nothing. So, well, I was literally shocked when we arrived at the North Pole. It was the August 31st, so the end of August, and this is the North Pole. Well, water everywhere with some patches of ice, but very, very, very thin ice. So this gives you can touch with hands the velocity in which these problems are happening. And that was for the Arctic, but until a few years ago, we knew that this was just for the Arctic, and the Antarctica was in a sort of steady state for the sea ice. So the sea ice in Antarctica is during winter time is very, very broad, and it has a lot of extension. But if you look in the last few recent years, it started to decrease since 2015. Is it that a trend? Is it a part of the variability? Well, we probably have to wait a little bit more. But I can tell you, last year in our station in Terranova Bay, the plane couldn't land because the ice was too thick, too thin. So, well, in 40 years it never happened. We'll see what happened in the future for the sea ice in Antarctica. What about biology and biodiversity? As you can see also from the graph on the left, there are mammals, terrestrial mammals in the Arctic. There are fishes and birds in Antarctica. Plenty of biodiversity. Is one of the richest places discussing about biodiversity. Of course, they adapted since a very long time to this unique environment. And of course, this adaptation is of interest, of course, if you want to study also biotechnological application, and also, as we discussed with Antonino before, astrobiology, because there are things that are very, very, very interesting and strange happening in the evolution in the polar region. It has a lot of implication about microorganisms as well, about the carbon cycle and the stability of this ecosystem. Of course, we don't know that much. I mean, these areas are very difficult to reach. Sometimes the species living in the Arctic and in Antarctica are threatened by the shrinking of the ice, by pollution, of course, and invasion of alien species. Of course, the water is warming, and so other species are popping in from the Atlantic Ocean, and we speak about the Atlantification of the Arctic, or also in the south, we see changes in the species, in the species of the Arctic species. Well, again, I told you that we are very close to some of the tipping points, threshold that we reach. I want to show you, this is a record taken from an ice core, a temperature record in Greenland over the last 120 years. Well, 120 years ago, we were in a period called the Hemian. It was a period similar to the one we are living in, an interglacial. So it means a period in between two glacial periods. And then we went, because of orbital parameters, so changes in the tilt of the axis of the rotation of the Earth, changing in the elliptic plane, in the motion, precession motion, and so on, we went slowly into an ice age. The amount of energy arriving on the surface at a specific point decreased during time. But that was not a constant cooling, you see. There was a sort of roller coaster with temperature went up and down. Every single jump, which are numbered, you know, there were about 25 periods like that, is called Dansgaard-Oeschger events, abrupt climate changes, changes in the temperature and in environmental condition that caused an increase in the temperature of 10 degrees in a very short period of time, less than 50 years, so spanning on a human life. So we were there already. Our ancestors were already spreading around the Europe and spreading around the planet. And again, after this period of time, we went through the last 10,000 years that you can see on the left with a very calm and pretty flat temperature. We never had abrupt climate changes in warm period of time if you look at the records, and that's for a sort of interplay between ocean and atmospheric circulation. So there are the possibility to have very, very important overshoot of a threshold. And from a physical point of view, a tipping point, is in a complex system, I would say, it is something when from a small change you have a huge or even irreversible change. Let's say if you keep it as a forcing the greenhouse gas concentration into the environment, you might have different responses, you know. You might have responses from the temperature, as an example, in which you, from a tipping point like that, from a forcing like that, you might have an increase, and then the Earth system re-equilibrate into a normal value, or you might have something which goes outside and very, very sharp increase in the temperature, for instance. And what happened in the past, when you take out the forcing on the right top side of the graph, when you take out the forcing, you can have many different behavior. You can even have the system that goes back in a slow way, that goes back very quickly, or it never goes back. So that is a tipping point and what we call irreversible changes. And because of global warming all over the planet, we had many tipping points. Imagine the forest in the Amazonia, but most of the tipping points happening into the climate system are located at the poles. So that's the reason why we are very much worried about that. And I'll give you an example, a little bit more than one example, and it is in Antarctica, on the West Antarctic region in the Pine Island Glacier, is a very important region. A tipping point can, we might have different behavior, I mean, different system states and response. In the first two cases, you have a linear large forcing and the linear and the small response, but then the system recover very quickly and go linearly back exactly at the same point where it started. Even in the second, on the second panel, we can have with a small forcing, a huge response, but linearly then it goes back. In the last two panel, I mean, we do have we can have small forcing where the system either with an hysteresis cycle doesn't go back into the original status. So when you push, when you give a forcing factor, when you increase the forcing factor, the system is no longer able to go back at the initial state. Well, we have it example, as I told you, in West Antarctica. Again, this is an example, very, very important, is called, again, Pine Island Glacier, where we had a very, very massive loss of Arctic ice, which has been eroded on the bottom of the ice shelf and lost mass very, very quickly in a short period of time. And this creates a cascade effect, because when you take out sea ice, you know, and then you have the ice sheet over here, you take out the sea ice, the dynamicity of the ice sheet is increasing and increasing. So the flow velocity of what is on top, it accelerate and accelerate and accelerate. So this is something we have to take into account in the current condition. So things are changing very, very quickly into the climate system. Again, I want to show you something which is happening already. Well, on the graph over there, you have the temperature increase. The blue dot means that is today warming above the average value of the pre-industrial value, is about 1.3 degrees. This is, let's say, if we will increase 3 degrees with future CO2 scenario, this is how the Greenland, the West Antarctic ice sheet, the East Antarctic ice sheet might behave. So they start to degrade very, very quickly. And we do have examples in the past, because we learn a lot from the size and the behavior of the ice sheet in the past. Again, I want to go back to what I said at the very beginning. We have 4 examples in the mid-Miocene 23 million years ago, and then 3 million years ago, 1.2 million years ago, and in the Hemian about 130,000 years ago. Well, in this case, the CO2 concentration were about 500 ppm, so higher, much higher than today. The temperature was about 5 to 9 degrees higher than it is today. And you can see on the left the global mean sea level rise that can be reconstructed looking at the corals and the coral beaches and the coral reefs and so on. We had we had glaciated Antarctica already. We had no Greenland ice cap yet at that time. Well, Greenland ice cap started to form about 4 to 3 million years ago, with a concentration of CO2 which were similar of the one of we have today, with a temperature range which was about from 2.5 to 4 degrees higher than the pre-industrial value. And look at the sea level at that period of time. It was from 10 to 20 meters higher than it is today. Then again, 1.2 million years ago, ranges of the greenhouse gases, CO2 were from about 300 to 400 parts per million. Temperature is in the range, the increase in the range that we have today, with a sea level of about from 10 to 20 meters. And this is what we have in the last interglacial, 120,000 years ago, with a temperature concentration below 300 parts per million. It was slightly warmer than today, and a sea level that it was about 5 meters higher than today. So look at that, with a scenario of 3 degrees and projected into the future, we had a sea level rise of about more than 20 meters. With a scenario of less than 1.5 degrees, we have a contribution of the Antarctic ice sheet that goes well above can go well above the 10 meters. So there is all that to say that there is a lot of uncertainty also in IPCC projection into the future, and I want to show you in a minute. So these are the projection that we might have into the future, that on the right, compared to what we have seen before, looking at the greenhouse gas concentration and the future temperature scenario with 1.5, 2 degree. Remember the Paris Agreement, you know, and keeping the temperature within the 1.5 degree or 2 degree, 3 degree, 4.4 degree, depends on the social economical pathway. So all these regarding the Antarctic ice sheet, the West Antarctic ice sheet is not completely considered into that. So that's the reason why we are more and more convinced that every 10th of degree matter for future climate. And again, if you look at the projection of the IPCC, this is sea level projection. You see, well, these are the future scenario at 2100 with a foreseen increase of maximum 1 meter in the worst scenario. But what you see here is in this dotted line on the left, you see what is called the low likelihood, high impact storyline. And this is exactly referred to what I've shown you before, to the instability of the West Antarctic ice sheet, because that will be crucial for the future, because if we will have an accelerated instability of the West Antarctic ice sheet, this climate trajectory will bring the sea level rise to much higher value than we can foresee today. Well, coming back to the last point, I told you the polar region are the grail for the race for the grail. So we are seeking very old ice. We want to understand what happened before these oscillation, and especially we are very much interested to look at this very layered layers of ice into Antarctica, and especially to a period of time which is called the mid-Pleistocene transition. With the previous ice core record, we arrived more or less here 800,000 years ago, which per se we saw all the glacial interglacial transition, CO2 fluctuation from about 180 to 280 parts per million, but we have no clues what happened before about the CO2 changes, because the only record we have is coming from the marine sediment records. And marine sediment records say that, okay, we do have oscillation, but there is a changes in the amplitude and frequency of this climate oscillation. We move from a 40,000 years world with a very frequent 40,000 years frequency and low amplitude to a new way of way of working of the climate with a much ample cycle and higher lower frequency, so about 100,000 years. This is not linked to the orbital parameters. I'll show you we have no clues about changes in the orbital parameters. Everything was like that, so it should be something inside the climate system, inside our planet. Well, it has a lot of implication, of course, for climate sensitivity, how the climate system reacts to CO2 changes in the future, and that is extremely important. Well, sorry, vertical axis is a proxy, a substitute to the temperature. I forgot to tell you, sorry. Is a isotopic composition of the little tiny shells that we have in the marine sediments. Foraminifera. We do measure isotopic composition of oxygen, which is related to the temperature, or better, to the size of the ice sheet, which is related to the temperature. So the lower it is, the colder it is, more or less. So it's cold, warm, warm, cold, warm, cold, warm, cold. Well, so we can reconstruct, this is a climatic record of the last 3 million years. And it changed the frequency, it changed the amplitude, and this transition, this specific place here is extremely important. Something changed within the climate system. We still don't know, and we want to know. But to disentangle that, we need to have a continuous measurement of greenhouse gases, dust, and temperature. And by the way, this period is also very interesting, also from ourselves, human evolution. There was a paper a few months ago, and Giorgio Manzi, a colleague of Sapienza, is one of the co-authors, in which they reconstructed the population, the human population during the last million years. And well, they discover from anthropological and biological analysis that during the mid-Pleistocene transition, during that period of time that you see what is called the bottleneck, for about 100,000 years, the humans' population was lowered down to less than 1,300 individuals. So for 100,000 years, the population of the planet was dropped down to about 1,000 individuals. So if we are here, it's just a miracle, I would say, of the evolution. After that, things change and it increase and decrease and increase. So that's an important thing, but that's a side effect. We don't know yet if it is linked to the mid-Pleistocene transition. As I told you, if we look at the summer insolation, so the amount of energy arrived on the surface of the Earth during the last 2 million years, it didn't change that much. I mean, this graph here, it gives you the amount of insolation, watt per square meter, so it didn't change that much during the mid-Pleistocene transition. Well, we can have several explanations because of that. One is tightly linked to geological or geochemical composition, especially of the northern hemisphere, and is tightly linked to the fact that in between the ice sheet and the solid crystalline rock underneath, there was a very silty and slippery sediments that didn't allow, before the mid-Pleistocene transition, to rise up huge ice sheet. So everything was having the flux of the ice sheet was pretty high. So no big ice sheet before the mid-Pleistocene transition. And when all these regolith with these tiny silty sediments have been completely eroded, the friction under the ice was higher, and so it allowed the ice sheet to grow up faster. Well, that's what our colleagues geologists say to us. We want to see that. So, but to see that, we need to have ice older than the mid-Pleistocene transition. And if you look at that, again, on the top, we have the CO2 concentration record over the last 800,000 years. This has been collected thanks to the European project for ice coring in Antarctica, EPICA. This is the temperature reconstruction that you see on the red curve that match together with the CO2 data. And on the bottom, the black curve is the benthic delta O18, again a proxy of the temperature taken from the little tiny shells of the foraminifera.
Does it make sense to ask what happens if you enlarge the lower scale?
Say again, sorry?
I don't know if it makes sense to ask what happens if you enlarge the scale, the horizontal scale.
Yeah.
You enlarge the scale, right?
Yeah, sure. But that's an age scale, so that's 1.4 million years ago. 1.2 is well. If I stretch it, yeah, yeah, sure.
If you enlarge the scale,
yeah.
do you still see the correlation between?
Oh yeah, sure. Yeah, definitely. Yes, absolutely, yes. The point is that we don't have CO2 data older than 800,000 years because there is no ice older than that. We do have a few data, as you see on top. You know, you see those CO2 data which are taken from again from marine sediments, not in a direct way. It's not a direct measurements, but to extract the CO2 data, they measure boron isotope. Boron is tightly linked with the carbon cycle into the marine sediments. Well, if we want to know something better about this very specific period of time, we need an oldest ice. So we went again in Antarctica, we went everywhere to look at a place where to find oldest ice. we need a place where we have a low accumulation, so a little accumulation, a flat place, because if the place is too steep, the ice flow very quickly. Not too thick, because if it is too thick, we have melting at the bottom. And if you melt the ice at the bottom, you have a mixing of the layers, so that's something that we don't want. So we went in many, many different places, and we find out that the place within that two red dots is most likely the candidate place. And we call, well, we have not very big fantasy, we call BeyondEPICA, so we want to go beyond the previous EPICA project. Well, we started to do that, we made more than 20,000 kilometers with vehicles and planes to find a place with radar echo sounding. We follow, you see those layers are layers into the ice that allow us to build up a model for the age, what we call an age scale, the age of the ice and the depth. This is the previous, the red one is the previous EPICA core, in which we have tie point, which is the red dots, and this is the model age that we are seeking and we are planning to have at the bottom of the ice. So the ice at the place where I've shown you is about 2.7 kilometer deep. We are drilling actually into that place. We started 3 years ago. Well, we started before COVID, then we had a rest because of the COVID. We started to drill in 22-23. We just finished the season a week ago, and we are today at 1836 meter deep. At the age of the ice there is about 200,000 years. We have at least one good season to go, at least 1,000 meters to reach the deepest part. And the deepest part, of course, is the most interesting, is where we are planning to find the oldest ice, the mid-Pleistocene transition. Well, this is more or less what I wanted to tell you. There are many different aspects in which, for which we are interested in polar matters and polar regions, and they matter a lot for us because, again, what happens in the poles doesn't stay in the pole. I told you I wanted to add another point to that, and this is the sixth point, and this science diplomacy. We do collaborate a lot with Chinese, with Russian colleagues, with many different researchers. And just to give you an example, in the middle of the Cold War in the 80s, when you know the Americans and the Russian, they were exchanging spies in Berlin at the Gebruke Bridge, you know, in Antarctica. French and American planes were landing in Vostok Station to refill the station. So the collaboration never stops. Scientific collaboration never stops, and it's not stopping even in these days in the spatial places like that. Well, I think I told you everything. Since there are a few students, I want to advertise the PhD program. We do have a national PhD program in polar sciences. Is based in Venice, actually, but we are a university from Messina to Trento that are participating to that, including some research institution. And it's done around 6 curricula. One, of course, on climate science, biology, ecology, biodiversity, solid Earth, human impact on the polar region, ocean and cryosphere, astronomy, space, and Earth observation. So all that, and we also have a tiny program on social sciences as well, because of course the geopolitical issue is a very big, is very important, especially in the Arctic. Well, I just want to leave you with this mirage. You know, is a fata morgana, is a how can I say, a reflection. These two things that you see are 2 towers. Is an Antarctic station based in Concordia, which is about 40 to 50 kilometers from the place where I took the picture. You can't see it directly because it's under the horizon line, but you can see the station reflected on the atmosphere. And when it's very cold and there is a stratification and the air, there is no wind, you can see the image of the tower upside down on the sky. Well, let me wish you, I mean, to think about that, to have a dream for the future like this mirage. And I thank you for your attention. And if you have questions, I'm here to reply.
Thank you, Carlo, for your very, very exciting and worrying talk. So, questions?
I think that what I'm saying is probably correct. There is a clear asymmetry between the northern hemisphere and the southern hemisphere. That should be correlated to the different fractions of people that live in the northern hemisphere to the southern, right? Well, the northern hemisphere is much more populated than the southern part.
More than that is due to the different way in which the heat is transported in the atmosphere and in the ocean. Of course, there is a much stronger impact in the northern hemisphere because of human population, but when you emit a gas, I mean, the gas goes everywhere,
yes,
especially
I mean,
short-living gas like methane.
In some sense, it vindicates the idea that human activities are the main source of this
Definitely, yes.
phenomenon.
Yeah, if you see, there are animation looking at the CO2 emission all over the globe, and you see clearly the asymmetry in the emission that you mentioned. This definitely, most of it is on the northern hemisphere.
Yeah, I have a curiosity. What is known about the effect of the inner Earth on climate? After all, need not be a stationary system, and there may be plenty of thermal energy or other sorts of energies that
definitely,
is
especially
with the inner of the Earth.
Especially on the other way around, I would say there is a lot of studies looking at the induced volcanism driven by the change of the weight of the ice sheet, you know. And this actually is here in Pisa. There is a group working on how the frequency of volcanic eruption is changing because of the warming and the melting of the ice or increasing of the ice. But regarding the innermost part of the Earth, well, no, there is no real correlation, I think.
There is no correlation.
No.
It has not been studied. There is no correlation, as far as you can tell.
Well, as far as I'm not a geologist, but as far as I studied, I mean, there is no real correlation in between the deeper layer of the planet, of the Earth.
I was wondering, during all the projection you've shown us, let's say the worst case scenario you showed us, does it take into account the, let's say, chain effect that would be triggered if we reach the point in which methane clatrate are released?
Yep. I know what you mean. Yes, consider that the methane, the permafrost, the frozen soil, especially in the Arctic, holds more than double of the greenhouse gases which is in the atmosphere. Yes, the future projection account for that as well. Although that is, there is a large uncertainty about the how much permafrost will melt in the future under certain conditions. And about that, we were discussing about viruses and things like this. When the permafrost melts, we have a lot of viruses and bacteria and fungi that get freed on the air, and it happened in the last few decades.
Thanks. Fantastic talk, a very inspiring one. So there is something that I'm not sure understood well when there is this point at the
Mid-Pleistocene transition.
The population, so this transition that the population, it's only few hundred of people. So, but how can you estimate that there was a population before and?
Well, this is anthropogenetist, I don't know how to call them, is anthropologists that did that, looking at the gene of the skull and remains and fossil that they found in different areas of the world.
So, but they say that there was this first 300 people, but not how many there were before.
No, they could study that because they have samples from let's say 2 million years ago, 1 million years ago. Then the bottleneck arrived, and then the increase of the population. Yeah, actually, is a paper in Science. This one it's published last year. I'm not an anthropologist, but they could estimate with a very good accuracy and precision the number. Well, in fact, you see, I say 1,300, they say 1,280. Well, I don't know whether they were 81 or 82. Not really, but there was a bottleneck. And it also surprised us because when we started this project looking at the mid-Pleistocene transition, we said, well, we must know what caused the changes in the frequency, you know, and in the amplitude. And then this paper came out, and we say, well, is that climate change linked to this one, or something else happened, you know, a pandemic or whatever? We don't know.
We don't know. So
we don't know at all. Yeah.
So you didn't see any climate change in that curve?
What we saw is the changes that we saw is before it was oscillating like that, a periodicity of 40,000 years, and then during the mid-Pleistocene transition, the frequency changed. We went to 100,000 years and more ample. Honestly speaking, I don't think
100,000 years
is double is more than double than 40,000. Yeah, is a lot. I'm not sure whether these longer and more severe ice ages were the effect. Well, we don't have proof of that. We don't have proof. We have to work much closer with the anthropologists to match the records.
Interesting, very interesting. Thanks.
Yeah, but it's something that came out. When we planned the deep drilling project to looking at the mid-Pleistocene transition, we didn't know about that. We didn't know about the bottleneck and the fact that it was there. But now, well, it's worth thinking about and discussing together.
Thanks.
So there should be a mid-Pleistocene big project.
It should be.
So the Earth was much hotter, you showed like millions of years ago, right? You were showing so do you understand all the mechanisms that cooled it down to...
Yeah. As I said, well, we can discuss later if you want, but basically the Earth, since it's during the last 4.5 billion years ago, always regulate the temperature. It's like a chronothermostat, like you have in your, well, like this one, you know. Like you set the temperature, and the temperature of the house is kept, of course, with a sensor within a certain value, or is oscillate like that. And the Earth did the same. Thanks to the CO2 emission from volcanoes and natural sources, thanks to the weathering effect, the fact that when the temperature goes up, there is a lot of humidity, a lot of water vapor in the atmosphere that withdraw the atmosphere in the atmosphere, and the carbonate and CO2 is taken into the sea. So it's more or less regulating the temperature like this. So it's a carbon cycle regulate the temperature and keep the temperature oscillating like that. But the cycle lasts for 100 million years at least, you know. So that's the reason why since about 60 million years ago, the temperature went down. And that's an argument of the deniers. You know, they say, well, it was 15 degrees warmer than today. Why we have to worry? I mean, we have to worry because we are living in this planet. You know, the Earth will manage anyway without us. That's not a problem of the Earth.
We have to worry because we are in that moment.
Exactly. We are living in this planet.
Just one final little curiosity for me. Now, the last 50 years, the culprits are clearly industry, population growth, and transportation, or whatever, you name it. Does the Second World War, if you go there and check that period, did the Second World War have an impact on CO2 and other productions? Did people, I'm thinking about all the bombing and explosions and all these things, including the
I don't know whether there was an impact on climate, but certainly there was an impact on the environment. You can look at very simply at the plutonium concentration in the ice. And if you look at the plutonium concentration in the ice, you see a huge increase in the layers dating during the nuclear bomb test, starting. Yeah. Or you can look at the increase on other pollutants, organic or inorganic pollutants like lead, for instance. Lead increased dramatically during the Industrial Revolution. Bullets and fuel as well, our generation certainly remember during the 60s and 70s the ESSO advertisement, put a tiger in the engine. Everyone remember, and the tiger is a lead, tetraethyl lead, and that was used as an anti-knocking additive in the gasoline, but being very volatile, it was spread around everywhere. And so we see in the ice clearly the increase of lead in the concentration, especially in the 70s and 80s. And when lead has been banned because of it is a pollutant and is polluting the catalytic converter as well, you see clearly in the ice the drop of the concentrations. That means that also, if we take action, the environment respond. It can respond quickly for short-living species like, plutonium or lead. It might take a little bit longer for CO2, because CO2 stays in the atmosphere quite a lot. We went above, I just want to give you an example. Paris, the COP that has been held in Paris in 2015. Well, the concentration, CO2 concentration was at about 400 parts per million, Now we are at 420 parts per million. So despite whatever we have said, let's go down, stop emission and so on, we are at 420 parts per million. And nobody inside this room, nobody living today in the planet will see CO2 concentration dropping again below 400 parts per million. Whatever we do, even if we stop today, immediately. Because it stays in the atmosphere quite a lot. Nevertheless, we have to take action. We simply can't continue like that.
Is it possible to obtain information about the trend in aerosol from the analysis of ice cores?
Sure.
Because it's one of the most largest causes of uncertainties. Sure.
Yeah, well, I didn't show everything, but in the ice you can measure a lot of things. You can measure greenhouse gases, you can measure the dust, and of course dust is one of the extremely important backscattering agent. You can look at chemical species, pollutants, but sulfate, for instance, chloride, sodium, and many different species. So you can disentangle the contribution in the aerosol coming from the marine source, coming from the terrestrial source, also coming from the extraterrestrial source. We published a paper in 2004 with a very nice cover in Nature. We measure the cosmic dust influx in the ice, looking at at palladium and platinum that are typically of extraterrestrial source. So we could measure the flux of extraterrestrial source falling into the planet thanks to the palladium and platinum in the ice.
I think that you can also measure beryllium-10, which is related to the solar radiation.
Definitely. We didn't speak about how we date the ice core. That's another big issue. dating of the ice core is really tricky. One of the things we use is beryllium-10. So far, most of the dating has been done counting layers, you know, visually or chemically, because there are species that goes up and down. But when you go deeper and deeper, of course, signal is a bit mixed. And now we are working with the stable isotope, absolute dating using chlorine 35, krypton 81, but we still need quite a lot of ice, because when you have an ice core which has this size and they ask you 5 kilos of ice, it's like to take a rib out, you know. So it's quite a lot. So, but we are almost there.
If there is no other question, I have one. Is there an age limit to apply for your PhD?
Yeah, welcome, Antonino.
Anyway, thank you very much, Vittorio.
So we have refreshments downstairs in Sala del Priore. You're welcome to join us, and the locals can guide the guests.